Hello everybody, welcome to this presentation named Study of Explainability Analysis Method for the LAMDA family algorithms in classification and clustering tasks. My name is Carlos Quintero and this work was possible thanks to the big contribution of the Professor Jose Aguilar Castro. In the schedule we have an introduction, objective, fundamentals, our approach, data set that we use in this work. Finally, we will show some results and conclusion in this work. In the introduction context, I can say that right now we have a lot of program or software in machine learning that can be implemented in different real-world cases. So the design, implementation, and use of machine learning methods has increased significantly. But jointly, the interest to know how the machine learning methods take and make decisions also increases too. In this context, artificial intelligence has considered three aspects. The first one is transparency, that is happen when the parameters of each model are easy for determine and justify. The second one is the interpretability. Is when the model is easy to understand for the human. And the third one is about the explainability. Explainability allow to understand why a specific output is produced for a particular input. But additionally, machine learning context provide different methods for explainability analysis, as such as LAMDA, that is a acronym of local interpretability, model agnostic explanation, and feature importance in others. In the algorithm that the machine learning we use, we have a LAMDA that is a acronym of learning algorithm for multivariate data analysis. It's an algorithm of machine learning that we use as such a classification context using lambda hat, and then clustering context using lambda RD. In both cases, classification and clustering, we have a good results according to the metrics that the test performance in clustering and classification tasks. Although we have many explainability methods, these methods do not provide the level of explainability at level of each class or group. Instead, these methods provide explainability in a general way. By before mentioned, we have two objectives. The first objective is the development of explainability analysis method for lambda algorithm. In both cases, classification context using lambda hat and clustering context using lambda RD. The second objective is the definition of a new method of explainability analysis by class cluster. In the lambda, the device basis conceptual in lambda, we have lambda is a fusion method based on global adequacy degree. In first instance, we need to normalize the individual through a min-max function for standardize the matrix of the data input. Then we have a marginal adequacy degree, MID, is a density function as such as Fusion binomial function and Gaussian function. Both functions determines how similar is a descriptor respect to the same descriptor in a given class. In the average, we have we can determine through this equation rho kg and the standard deviation through this expression that can you see. In the case that an individual is not assigned to any class or any cluster, this individual is formed part of a non-informative class, and this happens when the marginal adequacy degree is lower than this value 0.5. So in this case, the individual is not assigned to any class or any cluster. Next, we have a global adequacy degree that determines the adequacy of an individual to each class. This value is possible because we have a function according MID. T and is are aggregation function for the lambda, such as min max, product sum, hand measure, and dumbbell operator. Alpha is a exigency parameter, and then in the clustering tags, index is the max of a GAD for any class in the object, and a GAD of the non-informative class. In this slide, we show a scheme or a general scheme for lambda. We can note that in first time we have the determined marginal adequacy degree. Next, we have to determine global adequacy degree. For finally, we determine the level of the class that individual can be assigned. Lambda have some improvements for obtain best performance. In lambda has the first improvement is determine a non-informative class as number of existing classes, and the second one is determine a higher adequacy degree for obtain a best performance in classification clustering according to different metrics. In the clustering context, lambda RD have two improvements. The first one is an automatic merging algorithm, and then determine robust marginal adequacy degree using a Cauchy distribution. This improvement is to avoid the creations of many clusters. In the explainability based lambda algorithm, we have the next matrix, that this matrix is formed by MID and KP. MID is marginal adequacy degree for the individual and in the class K for feature P. Based in this matrix, we have two definitions. The first one is the importance of the feature P in the class K. This parameter represents the relevance of the descriptor P for the class or cluster K. We determine through this equation. The second definition is global importance of the feature P. This parameter represents the global average of the descriptor P for all class or cluster. Through this definition, we can determine the global importance, for feature and class or cluster. In clustering tags, MID is replaced for RMID and KP. So in both cases, the explainability method is the level of each class group and the global level in classical, that this one is the classical methods. We have different data sets that we use in this work. We have two data sets for classification, iris and dengue, and two data sets for clustering context, breast cancer and wine. In iris data sets, we have 4 features: sepal length, sepal width, petal length, petal width, and we have one target is classes: setosa, versicolor, and virginica. In this table, we have the metrics for performance in classification context, we can note that we have 96% of accuracy according LAMDA. We conclude that is a good result in this dataset according LAMDA algorithm. In this slides, we have the global importance according different methods of explainability, LAMDA, LAME, and feature importance. We can note that sepal width is the most important feature according different methods, LAMDA, LAME, and feature importance. So we conclude that the results of LAMDA explainability is very similar to the traditional methods. In this slide, we show the global importance of features for each class, and so we note that sepal width is the most important feature in class Setosa and Virginica. So this work or this analysis is the main explainability that is novel in this work. In clustering context, we have in this slides we have a performance in clustering context. We have the global importance features of the 5 most important features in cancer datasets. We can note that no-cut is the most important feature in global wave. We can note that LAMDA RD form 4 clusters, and we can note that the most important feature in 3 of 4 clusters is the feature irradiate, that is important is cluster 1, cluster 2, and cluster 4. So similar classification context, we note that this explainability is each feature for each cluster format in this context. Well, finally, we have some conclusion. The first one that we developed explainability methods for based in LAMDA in both contexts, classification and clustering tags. The second conclusion that our approach allows measuring the global contribution for each characteristic, but also allow contribution of each characteristic in each cluster or class, being the main difference with respect to the other methods, being the main contribution in this work. With other methods, is a general ranking of the relevance of characteristics that very similar to those obtained with the classical explainability methods. And finally, as a future work, we must make more experiments with other datasets, with other dimensions of features and number of records in others, and also more comparisons with other feature-oriented explainability methods. Well, finally, I want to thank your interest in this work. Bye-bye.